All right, recording started. Today we're doing topic 42, which is the last topic. Technically, there's topic 43. And to be honest, not important for either phase 4 or the capstone, but I do recommend, like, if you find yourself having a little bit of extra time, either like while you're working on your capstone or even after graduation, those labs will kind of link you to Amazon's tutorial of using AWS. And it's basically how you use AWS's version of Jupyter Notebook and machine learning. So I feel like going through that is more than sufficient. I don't want to like just repeat everything that's on there. So that's what topic 43 is. So today will be our last content study group. Tomorrow we'll do our project walkthrough. And of course, I'm going to cater it to like all of the projects of the folks in this cohort. So yeah, I think everyone has already told me what they're working on, so that's good. So today, 4 main things we're going to talk about with regards to wrapping up neural networks. First, pre-trained networks. I'll talk about that in a little bit. Next, we're going to talk about a GridSearch / Talos. So Talos is another library that pretty much does what GridSearch does, find the optimal hyperparameter combinations for specifically Keras or TensorFlow neural networks. We're going to talk about saving your neural networks because it's a little bit different than like, pickling a model. And then finally, we'll go through a conceptual slideshow of recurrent neural networks. And recurrent neural networks, we don't remember, are the kind of forecasting neural networks. So you can use it for time series, for anything that is forecasting. So things like text prediction or any sort of sequential generation would use an RNN, and we'll talk about that later. All right. So actually, let me clean this up before we start. Okay. So first, pre-trained networks. These are things that if you're doing a neural network project, and it's also not just for images. I'll show you all some examples in a little bit. But a pre-trained network, which is also known as a convolutional base, if you're specifically doing convolutional neural networks, basically consists of neural network layers that have already been trained on very general data. So for images, these layers have already learned general patterns, textures, colors, etc., such that when you feed in your training data, certain features can immediately be detected. So what's happening here is feature extraction. So basically what happens, depending on what pre-trained networks you're using, we're going to use one in a little bit called VGG19, which was trained on a bunch of very generic images. So like different nodes have just learned different things to detect in images. Once you feed in your training data, you have those weights. It already knows, okay, in this image, we have positive coefficient for, I don't know, dog fur, and then negative coefficients for something else. Like maybe there are no like, I don't know, buildings or structures, stuff like that. So having pre-trained network, one, can really boost the learning because already a lot of the basic stuff has been learned, and your neural network could then focus on doing like the main things that it needs to differentiate for your data set. So we'll talk about doing that in a bit. And then typically within this process, which we're going to walk through some code right after this as well, you're going to add your own final layers to train the network to classify or regress based on your problem. And this is basically the fine-tuning component. So when you're using pre-trained networks, it is a combination of feature extraction and then fine-tuning. So here's a list of pre-trained networks that exist within Keras. There are a good few. They're all trained on different things. The one that we're going to talk about today is VGG19. So if you look over here, it comes from here, I think. I think it comes from this one. And it was trained on like a bunch of images. I forget what exactly, but it's very, very general images. So it recognizes things like colors, textures, edges, stuff like that. So there are a lot of readings available online. So if you're doing a very specific kind of problem and you're thinking, okay, which of the many pre-trained networks can I use? Maybe some reading can help. But usually any pre-trained network does boost your initial learning by a good bit. So some of the more popular ones, VGG 16 and 19 are very popular for convolutional networks. InceptionNet is another one. Anything with the word inception is one that I've seen used a lot. And it's not only for images. You can think about it in sense of like even dense networks, especially when you have a lot of like maybe text or just a lot of rows, there are pre-trained networks on other things. But for the most part, because images kind of have these like general features that exist throughout all images, like colors, textures, these very general elements, probably most used for images. So all of these are pre-trained networks that you can use. All right, so to demonstrate the utility of pre-trained networks, we'll compare model performance between a baseline model and a model using a pre-trained network. Although we're going to use a fairly simple, a very, very simple example. So I'm not sure if the numbers will be different, I forget. Okay, so to use a pre-trained network, and again, we're gonna download, the pre-trained layers of VGG19. And to do that, you really just need to import it out of Keras because it exists within Keras. So that's really convenient for us. So to add pre-trained layers, you first have to download the data. So the first time you run it, you actually have to download data and it'll do it automatically for you once you run this. And there are two important hyperparameters to use here. First, include top, true or false, and also the input shape. So you can actually adjust the input shape depending on the input shape of your images, and it'll automatically give you a set of weights that matches the input shape of the images that you are eventually going to feed in. So for this case, my input shape is going to be 224, 2243. So to look at the pre-trained network, you can actually see that this instantiation of VGG19 is a bunch of layers already. So we did this model summary in the past. Actually, let me pull up what we had last time. So it's called first neural network. All right, so last time when we did model.summary, we had like, in this example, just 3 dense layers because we did sequential add dense, add dense, add dense. Over here, when we did that, just looking at the pre-trained summary, automatically you have all of these layers. So you can see here, we have a bunch of convolutional blocks. So you have this input layer first, but you have like convolutional 1, 2, 3, 4 of different sizes as well, 5 convolutional blocks with so many parameters. It includes a flatten and 2 dense layers and makes a prediction here. I believe this is pre-trained on like 1,000 classes of images as well, which is why when you first download it, you have 143 million trained parameters. Now notice here, we already have the predictions layer, but how does our network know what the predictions are? Now we have this here because we did include top equal to true. So I put a note over here as well, just in case you're using this code. You want the version which is include top equal to false. So let me hide this output. Well, I can't hide it in Colab. But anyways, here we have include top equal to false. And I'm just gonna run the same thing again. And when I have include top equal to false, you can see that the last layer that we have here is the pooling layer. So because of that, it is not training the nodes that will contribute most to your classification or to your regression. That's mainly because in the structure of this neural network, it is the 2D layers, like any of these convolutional 2D, max pooling 2D layers. Those are the layers that are doing the feature extraction. And then we're just going to add our own layers because these, these are basically trained for these like 1,000 classes. So we don't care about the 1,000 classes, we care about whatever our classification problem is. So with that, once you have this one, and remember that we're running include top equal to false, and I should have named them the same thing, but they're both called pre-trained. But the one that I just ran is the one without the dense layers. So right now, pre-trained summary looks like this. What I'm going to do is I'm going to add all the pre-trained layers. So I'm instantiating a sequential model, adding all of the pre-trained layers, and then I'll talk about this in a little bit. But I'm going to also add my own flattened layer, 1 dense layer, and my softmax activation layer for whatever my problem is. So what I'm doing here is I am freezing the layers. So those weights in all of those 2D layers have already been optimized for detecting things like, colors, textures, all of those very general things. So we actually don't want those layers to adjust themselves. So because of that, we're actually going to set the trainable attribute of each of those layers to be false. So for layer and CNN layers, this also has to be done in the right sequence. Add pre-train first, set the trainable equal to false, then add the rest. So now when our model trains, it is only going to train this dense layer. So what's happening here, if we look at for layer and CNN layers, print the name and print whether it is trainable or not, you can see that the VGG19 layers are not going to be trained. And what's going to be trained are the flattened layers, dense 2 and dense 3. Any questions about this? Actually, let me quickly do a dot summary so we can see. Cool. So here, this is what we have. We have VGG19, which is now functional layers with this number of parameters, but they're non-trainable. So this number matches over here. And now when we're using this pre-trained network, we are not making as many updates. It will be a little bit more efficient as well, because you don't have to back propagate your errors through all of those layers. And it only needs to train, well, relatively small, but it'll only need to train like 132,000 parameters. So with this, you can just compile and fit your model. I took out the examples here, I think because it was not working, but it will work for you all. Any questions about pre-trained networks?
I have a question. Sorry if I copy this, but let's say the data that we feed through doesn't have the same pixel. Is that going to be an issue or no?
So not an issue. So that's why you can actually specify the input shape to whatever your images are.
Got it. Okay. So it doesn't really matter. We can just change it to what we need to from the very beginning. Okay, cool.
Anything else? All right. Sorry, I don't know if y'all can hear all the cars, but that's just, I guess, New York things. Okay, so that's pre-trained networks. I would say that, oh, this is a good time to actually talk about for the project, if you're doing the neural network project, there's very little EDA that happens for CNN, for any image classification project, because there's not too much to do exploratory data analysis on, because it's all images anyways. Typically, people just do show the class balance in like a bar graph, pie chart, something like that, and then show a few examples of images of each class. And that usually is enough for an image classification EDA, for those of you who are working on that. So the main thing of this project is to just look at different iterations of neural networks. I forgot if I talked about this last week. I'll talk about it more tomorrow, but basically I want to see at least 4 meaningful iterations of neural networks for this project. The first neural network could be classifying with multi-layer perceptrons, so not even going into the convolutional layers. You can just take your images, turn them into like one long array, not 2D, use that as a baseline model, perhaps run a baseline CNN model. You can include a pre-trained network for a third model, and then maybe a GridSearch model as your fourth. And those are your 4 CNN models for the image classification project. So that's kind of what that project looks like, in case anyone was like, all right, so what do I do here? Cool. With that, any questions? I will talk about it a little bit more tomorrow. And I know as you all get into more of the project mode, I'm sure you'll have questions as well. Cool. All right, so next we'll talk about GridSearch with Keras. GridSearch with Keras, this library I'm going to show you all is called Talos. And this is actually the reason why I'm doing this in a Google Colab notebook, because as you all know, for the past few weeks, I've had Python Jupyter Notebook issues. So if your Python version on your local computer is 3.8 or later, Talos might not work the right way. It just has to do with like different dependencies. So if you're running into those issues, I recommend that you do your neural network on Google Colab. It is faster anyways, and I'll show you why you don't have to worry about like your kernel dying and stuff like that. So technically there are 2 different ways you can do grid search. One, you can actually use scikit-learn's grid search. I personally don't use that method because there's like, to use that, and here's actually a quick example, you have to create a network object kind of. So basically you're creating this function that constructs a neural network. You have to wrap it in a classifier object, do that. I mean, you follow these steps, it will work absolutely fine. I've had students who have figured this out on their own for the project, so that's great. Especially if you don't want to learn like a new library, and if Talos is giving you issues as well, then you can totally use this method. I'll show you why I like Talos. So with this example, Talos is great because it lets you tune it without having to create this like classifier object. And it also automatically outputs your parameter combination scores into a CSV file. And that's really, really neat. I've linked the documentation over here. So I'll show you the example of using Talos with this very, very simple neural network that we did for our first neural network study group. So here I'm importing Talos after pip installing it, and I actually just re-pip installed it, so I know it definitely works in Google Colab. Have all of these are not new to us. Do my train test split. And the main thing they have to do is just define a quick function. And the function basically will tell Talos where are the things that I want to tune in my neural network. And so this can be a little bit confusing first, but let's just say out of all the things I want to adjust, or I want to test the different parameter combinations for different activation functions, number of nodes. Here, what else do I have? Dropout, how much dropout do I want? And remember, dropout is actually how much you, it's sort of like a regularization layer, if anyone doesn't remember. I also want to test different optimizers as an example. Pretty much anything that you can change in a neural network, you can change and you can make a hyperparameter that you want to tune. The only thing that you can't tune with using like GridSearch or Talos or something like that is if you want to change like the general architecture of my network. So what it's going to do is it's actually going to say, all right, usually this is where I put the number of nodes for my dense layer. And it's just going to look down here saying, okay, I'm going to test 12, 20, and 100. But there is no functionality to say, all right, I'm going to have this layer. And then I'm in another example, I'll have like 5 layers versus 3 versus 1. So that's not something that you can test using Talos, but it tests things within neural networks that have the same architecture. So anything that has dense, dropout, dense layers. Okay, so with that, anything that you want to tune, you basically make that a key in your params dictionary. So here's my params dictionary. I'm basically tuning 5 different things. So I'm tuning the dropout, number of nodes in the first layer over here. So I call it nodes 1. Optimizers. So optimizers here, I'm going to test atom and stochastic gradient descent. And activation 1 and activation 2. I wanted to see whether ReLU or TANH works better here, or ReLU versus TANH works better here. Another interesting that you could do, you can actually set this. Let's say you don't want the activation layers to be different, or you don't need them to be different. I actually maybe then can just have activation 1 for both of these. I don't even need this activation 2 in this dictionary anymore. Just both activation functions for the 2 layers will be the same. But just to show the functionality, I can test, they can end up being 2 different activation functions working the best. That could be how it is. Within this function, you also have the compile and fit steps. So here I'm compiling it here. You shouldn't change the loss function as well. So that's why that's not changed, but you have that there. And then you have the model.fit as well. And when you're returning, it's important to return the output as well as the model itself. So I'm not going to run this, but this also doesn't take too long. This one took about 1.5 minutes to run 72 different iterations. But here what I'm doing is I'm using the talos.scan method, give it my X-train and Y-train. Now this is something that's really, I don't know why it's like this. It didn't used to be, to be honest, but it needs to be dot values if you're using a data frame. Your params are your param dictionary. The model is going to be the function here. So dense network, that's where this comes from. And experiment name equal to grid. I just call it grid for GridSearch, but basically the experiment name will basically be the name of the folder that it automatically creates to output results. So that's really cool. All right, so after I ran this, and this took 1.5 minutes, what you can do is you can actually extract the best model by accuracy, for example. And if you don't remember, for metrics, you can actually have it take into account multiple metrics if you want it to. So I could look at both accuracy, F1 score, maybe recall, precision. You can do all of that too. So with that, I do this in Google Colab. So you can see here, it basically has created this grid folder that has a CSV of my results. So what's really nice about this is, for whatever reason, if your computer just stops, like it stops, let's say out of 72 iterations, it only does 30 and something happens and it like cuts off, it actually will save those 30 iteration that it's already done. And so it actually overwrites the CSV with every single iteration. So you won't have to rerun stuff if you don't have to. So I'm just reading in this CSV. I just copied the path. This is today's date. And I think that's like the timestamp or something. That's not important. But But basically, I can sort all of my values by validation accuracy, and I can take a look at my results over here. So these are my results. I have basically it's telling me that the best combination of hyperparameters is tan-h for the first activation function, ReLU for the second, 0.1 for dropout, 100 nodes, and SGD as my optimizer. So that's a quick and easy way, in my opinion, to do a hyperparameter search for your neural network. Cool. This also works locally, but it's just like Talis has been having, or a lot of libraries have been having issues with later versions of Python. With that, any questions? Cool. All right. So the next quick thing that we're going to do is saving your model. So saving your model is slightly different again from like saving a scikit-learn model. For scikit-learn models, we learned that we can just pickle our model. But when you pickle a neural network model, what happens is it actually only pickles the architecture of your model. And when you like read in the pickle of your neural network, for example, it actually will have none of the weights saved. You just have to still retrain your network all over again. And that's not the point of saving your model. So when you're saving a model in Keras or saving a Keras model, and let me just run this one super quickly, just set fewer epochs. Let me run this. This is the same example that we had from the first one. This is using the Pima Indians data set that we had last time. So cool, we're predicting well enough. These are the steps I used to do. There are built-in save functions within Keras, so that's very neat. We have literally model.save, but on top of that, you have model.save weights. So you just have to remember to do these two things, and then you're set. So the file extension is H5. I honestly don't know what H5 stands for. I never looked it up, but the go-to extension is .h5. And from there, these are the saved models, model and model weights. Within that, if you wanted to use this in a different notebook, or if you want to use this somewhere else, maybe you want to put it on a front end in the future, you can import the load model method from Keras, and you can load in model.h5, model weights.h5. So first you have to load in the model to the variable. This variable is called my model. And then when I want to add the weights to that, I do my model.load weights. So that is done. And just to show that it is being used, I'm going to put in my test data again and see this is my model that wasn't used, this variable name wasn't used before. When I run this, I have a 70% accuracy. So you know that this was trained at some point. All right. Any questions about saving the model? All right, so I believe the model should be saved. Oh, I didn't go into, oh, here we go. So the model is saved here, model.h5, model weights.h5 as well. All right. Any questions about any of the stuff we talked about so far before we get into recurrent neural networks? Okay, so recurrent neural networks is another part of our curriculum that, well, it's not part of the curriculum, it's part of the appendix of the curriculum. So because of that, I don't expect to see this in any of your phase 4 projects, especially, and this would be most relevant to those of you who are doing the time series project. So I'm not expecting to see any of this, but if you have time, feel free to implement one. I've linked a bunch of examples here. Pretty much like the main thing, I wonder if there's like a good example that we can see right here. The main thing that you have to do is just, it's a different layer type. So you can see here, instead of like a CNN layer or a dense layer, it is just an RNN layer. So that's what's different about it. And you just have to figure out the input shape. I would say read through these articles. They do explain it pretty well, because this is how I learned how to run recurrent neural networks. So I have a few examples over here. I'm going to go through this slideshow that just talks about conceptually what are RNNs doing. And on top of that, there's this subset of RNNs known as LSTMs, which stand for long short-term memory networks. And that's actually one of the most like cutting edge. People use that one the most, especially in like finance predictions, like stock predictions. And we'll talk about why maybe those work a lot better. Cool. So recurrent neural networks, the use cases for recurrent neural networks, we'll talk about that in a bit. But the whole idea of the recurrent factor is learning sequences, because so far when we're doing something like regression or classification, sequence is not really part of it. Yes, in time series, sequence is what we're learning. That's why when we talk about like things like seasonality or overall trends, that has to do with the sequence of your data points in chronological fashion. So sequence learning is a pretty big field within the field of machine learning. So sequence learning doesn't just look at a collection of items and their like individual characteristics, but an order as well. So ABC, for example, would produce a different outcome from ACB. So several things to start thinking about if you're considering using some sort of sequence learning in whatever project you encounter in the future. One, how can each element be represented either numerically or as a vector of maybe its prior parts? And sequence length. Is the length of a sequence variable or is it constant? As an example, if you want to think about making stock predictions, and we were using traditional time series models like ARIMA, things like that. If I'm choosing an ARIMA with the order 212, sequence length and what matters are the past 2 lags. So in something like that, the sequence length is constant at 2. Whereas maybe in some cases you want it to be variable, like with text prediction, for example. Let's say when you have text prediction, as you type in more words, you will take in more inputs because you'll have more context and a better understanding of what should come next. So that's an example of variable sequence length. I mean, we're not going to get into like all the depths of this because it is, I would say, like a whole nother boot camp to get into deep learning, but those are like conceptually things to think about. Okay, so some examples of sequence learning, and some of this might look kind of familiar. Frequent pattern mining. So frequent pattern mining is very similar to what we are doing when we were creating word embeddings, because we're kind of learning the meaning of words through what happens, what other words typically appear adjacent to it. So frequent pattern mining is an example. If you think about like predicting very sequential things like stocks, for example, maybe every time you see one pattern, something always goes up or down. That's also an example of pattern mining too. ARIMA is kind of, as I mentioned, sequence learning as well. Markov models, which are probabilistic models. There's actually a good bit of appendix material on Markov models, I believe back in phase 2. So if you're interested in more like probabilistic models, the probabilistic meaning like something that's more similar to naive Bayes and isn't really like a learning model, that's there. And then there's also sliding window models. So sliding window models is a subset of frequent pattern mining. Very similar, basic word embeddings are sliding window models. All right, so why isn't a multi-layer perceptron enough for sequence learning? So let's take a simple example in univariate time series. Why is a multi-layer perceptron model not enough? So one of the main considerations of like why people started to conceptualize different kinds of layers or different kinds of structures for layers is input shapes. So the input shape of a time series is not always consistent, right? As I said, like with the example of not even just stock data, but I think word data is a little bit easier to think about. Like the more words you have, the more inputs you would want your network to allow to take in, just so you have more information. And a regular MLP just doesn't work like that, because if you just give it like a bunch of maybe just zeros, it's not really taking that sequence into account as accurately. So even if you don't want to use a recurrent neural network, you have to be very, very careful about how you're treating your individual inputs. So that's where RNNs kind of have to step in. Cool. So recurrent neural networks, and the little thing that makes it different from our regular feed-forward networks is this new structure of things coming back within a node. And I'll have like a few very, they're kind of technical looking diagrams, but hopefully like by just seeing bits and pieces of these, it'll start to make a little bit of sense. RNNs are also very, very technically advanced, so you're not expected to like fully understand how RNNs work by the end of this bootcamp at all. But I think it is helpful to just know that, you know, neural networks can be used in other ways other than the ways that we've talked about in curriculum. So basically regular forward feed neural networks like this one over here, very similar to basically all the ones that we talked about have been looking like this. They all have an activation function that's fed all the inputs and then goes into the outputs. Very, very straightforward. The data just goes one way. RNNs have a recurrent activation that's also forward propagated and is fed from the output of the previous step in the sequence. So what happens is, let's just say, okay, I'm making a forecast for the temperature tomorrow. And I want my model to be able to forecast temperatures for the rest of the year, as an example. So let's just say I forecast some temperature for tomorrow. That forecast of the temperature for tomorrow should also play a part in the forecast for the temperature 2 days from now, if that makes sense. So is the fact that, okay, I have an output, I'm going to take that output back in to make my future predictions as well. And that mechanism of, how much information is being kept or how much information you want to disregard from these new predictions, that is like a whole nother thing. We'll talk about that when we get to the LSTM portion. But in just thinking about this new structure of data that is being output is being fed back in. Does anyone have any questions or thoughts about that? Okay. All right. Oh, one quick thing to mention. I talked about activation functions last week for recurrent neural networks. Hyperbolic tangent, TANH, is always used as the recurrent activation function. And it's very useful because it does go positive and negative. Where do I have? Oh, I don't have that diagram open right now. But if you remember the graphs of the different activation functions, TANH just allows to go negative. Sorry about all the noise, guys. Okay, so different kinds of RNNs are represented differently. And instead of having that diagram with all the circles and all the arrows and the nodes, if you get into a recurrent neural network course, sorry, let me close this for a bit. Okay, hopefully that's better. Instead of seeing our usual, with the circle and the arrows, another way that you'll see if you take like a recurrent neural network course, they actually will represent their recurrent neural networks like this instead. So again, the variable input, so you can see here, this is an example that would just take in one input, output one input, maybe like univariate time series would use something like that. One to many, if you're using text prediction from one word and you want it to spit out a bunch of multiple words afterwards, this is what it would look like. Many to one, if you, let's say, want to take in, I don't know, the past however long of stock data and just care about tomorrow, that's an example. Many to many. Many to many is interesting because it can be represented in different ways. One really cool example that I've heard, I cannot confirm, but I've heard Spotify playlists. If anyone has those, like Spotify apparently has some like automatically curated playlists where depending on what songs you play, it will actually maybe automatically add songs at the end of it or something like that. That is, I've heard, I don't know, I can't confirm, but it sounds like it could use something like a many-to-many recurrent neural network, because depending on what songs you're skipping, depending on what songs you're fully listening to, the order of songs, it can actually produce things like that through a structure like this. Cool. I know this gets a little bit abstract and technical, so let's just talk about some use cases. So as I mentioned a couple times, one of the most common use cases, or two of the most common use cases, I'm going to go a bit out of order, NLP. So you can actually use RNNs for predictive text, sentiment analysis as well if you're looking at things in sequence. Multivariate time series forecasting. So this is the other very common use of RNNs. So basically you're giving it, not just the stock that you're trying to predict, but maybe some exogenous variables. You can set it as an RNN too. You can also do recommendation systems, especially when it's something that's sequential. Maybe you want to recommend an item based on the last 10, 20, 30 items that a person has bought. So that is a use case of RNNs and recommendation engines. Audio interpretation. So I am much less familiar with this versus other numerical data, but apparently if you like analyze the waveform in a certain way, you can feed it into an RNN and it can do some sort of audio analysis, either output like overall stats of the sound file or things like that. It can do image recognition as well, especially in like a video. Or actually, this is kind of like, these two are kind of in the same point. You can kind of do analysis on videos because they're kind of like recurrent CNNs. So by combining the two, it's very complicated and will take a very long time to run. But theoretically possible, and I'm sure it is done in like some of these big companies that do analyze video clips. Cool. All right. So for propagation in a recurrent neural network is completely different. Well, the equations look similar, but what's being propagated is different. So actually, let me not use this one. There's another one that I think is a little bit better. Okay, I'll talk about this later when we get to LSTMs then. Oops, let me go back. All right. So before even you get into setting up an RNN, it's very, very important to think about how's your data being represented and that the sequence makes sense. Very likely, if you do decide to use an RNN, either for the capstone project or even for this time series project, the structure will be pretty straightforward because I'm sure that you're probably going to be using it for time series in this project and maybe things like text analysis in the next or text prediction in the capstone. So the structure for that is much more straightforward. If you're doing something completely different though, my suggestion is just look up similar examples of projects being done, see how they set up their data, understand that first, and then come up with your own variation of doing that, because it is quite hard to conceptualize how do I vectorize my input data. So I don't want to get too much into this. This is not an RNN course at all. Okay, so I talked about this. I showed an example really quick. You're using Keras, and simple RNN is the layer that you would use. So leveling up from RNN, they're not really leveling up, but a subset of recurrent neural networks is LSTMs, which stand for long short-term memories. So RNNs, where it falls short is when you don't have like seasonality, or if you are really trying to make forecasts very, very far out, RNNs have shown to fall a little bit short. So that is something that's not as good. So using this example, I'll talk about this first. Take this sentence as an example. There was a castle in the mountains on a river across from the valley where the king's army was marching. So some obvious connections that an RNN would see are kings and army, because the words are right next to each other, army and marching, because yeah, there's like one word separating the two. However, castle to king, where castle is like here, and I don't know how many words, maybe like 10 words after, then you have king. So this should be an obvious connection, but is too separated by other words. So the model has basically forgotten that there was a connection between castle and king. So maybe if you wanted to, let's say if this was our only training data and we wanted to talk about castles and we wanted our model to output some prediction of what word comes after castle, king would likely not be there as much. So with this sentence though, castle is a very important context clue to figure out what the sentence is talking about before even getting to, you know, the king's army was marching. So that's something that RNNs fail at or don't perform as well at, and that's something that LSTMs are a little bit better for. So LSTM stands for long short-term memory. So it basically talks about the memory across a sequence, and it works. I mean, the theory behind why it works better is because of the diminishing gradient problem within recurrent neural networks, which I think now not worth talking about, but let's take a look at the structure of an LSTM. So within each LSTM node, it is very complicated. As you can see, this is actually a single LSTM node. There are several gates. So the most important gate that's being introduced in an LSTM that wasn't in an RNN is a forget gate. And that's basically an additional parameter that tells your model what information should I keep, what information should I throw away. It's literally learning, okay, next time I see this word is usually not important, so I won't save any weights for this. This word probably provides a lot of context. I want to remember that this word occurred how many words ago. So the forget gate is probably, I think, the part that makes LSTM the most powerful part. There's the input gate, output gate. Those are very similar to our usual nodes as well. So vectors are going into all of these gates, and they all have weights and biases associated with each, and they're all learned in backpropagation. So there's very, very little, aside from your pre-processing, again, not too much work to do. Black box model, it's figuring it out on its own. And so it's gonna learn based on your training example, all right, what words or what patterns of sequences are good indicators of things to predict in the future. Cool. I know that was very, very abstract, but does anyone have any thoughts, or you're just like absorbing information? That's also perfectly fine. All right. Cool. So to end off, these are a bunch of resources that I highly recommend. You'll see that in our appendix, where it's the RNN part of our appendix, they also mentioned something called GRUs, and GRUs are very similar to LSTMs as well. So that's something that you might come across. And there's also bidirectional RNNs that kind of go both ways, so you can kind of not predict backwards, but you can predict different, I guess, scenarios is one use case. So you can do that. Here's a bunch of resources. So if you're truly interested in deep learning, and I know we barely scratched the surface with deep learning in this course, but there is like a famous deep learning Coursera course. I'll have it linked out to you, but it's by Andrew Ng. He's the founder of Coursera. He's the deep learning master. And so a lot of what I know is from his course as well. For neural networks, I don't know if any of you have like found this as to be a helpful resource, but for building RNN models, there are a bunch of YouTube videos of people just live coding models for their projects using Keras and stuff like that. So I linked videos there. There's some Russian guys talking about it too. There are guides to LSTMs, and there's like a very famous blog post on recurrent neural networks as well. Again, I do want to highlight that this is not part of our main curriculum. It's like, I think this slideshow goes more in depth than the readings do in our appendix as well. So really not necessary, but I do think like the implementation is the easy part for neural networks. As you all saw, like the math is very, very convoluted, but implementation is the easy part. So if you can, or if you have time to implement like any RNNs for your capstone or for this project, I do recommend it, just so you can throw it on your resume or something. But yeah, with that concludes our course material for study groups. What a big milestone. Tomorrow I'm gonna go a little bit more in depth into the projects. I'm pretty sure, I think I've like touched base with most of you on like what project you're doing. So I'm going to kind of like re-weight each of like the 4 topics based on that. So I'll do that tomorrow. Come with any project questions. I guess the biggest thing to flag is that our phase 4 presentation date is going to be next Wednesday, the 17th, if I'm not wrong. Let me double check real quick. But yeah, any questions so far while I look up our calendar?
Yeah, I had a quick question. So recurrent neural networks, you can, if I'm correct in what you said, it can be used in any like NLP or recommendation system, or
Yeah, specifically, you would use a recurrent neural network if you want your output to be based on a sequence. So if you want it to be based, like if you want something to be like in some order. So yes, recommendation engines, we've talked about many different kinds of recommendation engines, but specifically, if you want your recommendations to be like, all right, in the past, this person watched this video, how do I decide what comes next? It's based on my watch history.
got it. All right, thank you.
You're welcome. So yeah, in 2 weeks, we'll actually have 3 study groups next week. Well, not really study groups, but we'll have 1 office hour right before the presentation. Presentation will be on the Wednesday, and actually on Thursday, just so that we can get right into it, we'll do a capstone kickoff on the Thursday. So I know it'll be, I mean, y'all should be wrapping up the projects by then, hopefully. So I want to do a capstone kickoff before the weekend, so you can all be like thinking about your problems. I know some of you already started to talk to me about your capstone ideas, but this project first. Cool. Anything else?
I had a question. Yes. Can you, for like your GridSearch, quote unquote, when you're doing an RNN, and let's say I didn't know, like I know there's a couple different preset models like the VG16 or the VGG19. Could I put that in the model and also run it with the various like freeze frames and then making sure like, is that even a possibility? That's a little too much.
I think, well, you can't you can't have it search through the different pre-trained networks because those are different architectures. However, you can have it as part of a network that you're grid searching. So what I would do instead is like, instead of just doing this here, I would actually like add the, wait, where is it? Yeah, I would add the pre-trained in that function here. So I'll do like add pre-trained as there. But then, yeah, those weights, yeah, and then you'll do the free steps in here as well. But yeah, you can't test different, you would just have to run multiple grid searches, unfortunately, because that is like changing the structure of the network.
Got it. Thank you.
You're welcome. Cool. Anything else? All right, well, if there's nothing else, well, congratulations on finishing out all of the like content study groups. We have a lot of office hours ahead of us. We have, well, the project kickoff tomorrow, but I know a lot of you have already started looking at the project, so we can also have some office hours for questions. We can use up the whole hour. And then, yeah, next 2 weeks will be office hours. Capstone time will all be office hours as well. So don't worry about that for now. We'll talk more about that in the coming weeks. All right, if anyone has any questions, please let me know. Really, I think I've said this a bunch of times. For this project, my intention is for it to be as smooth and as chill as possible. Like if you all like my ideal situation is you all just like complete the project early and really start putting the main bulk of your focus on the capstone. So please feel free to meet with me. I think I've told some of you, but like since my full-time students graduated, I have a lot of free time. If you've like seen my calendar or like my scheduling link, I have a lot of free time right now. So happy to take like extra one-on-ones, talk about the project with more depth, do all of these things. So yeah, if anyone has any questions, you can Slack me or schedule one-on-ones. I am honestly really bored. All right, if there's nothing else, I will talk to you all tomorrow then. And we'll talk more project details tomorrow. Cool.
Thank you.
Good night, everybody.
Have a good night.
Yeah, have a great night, everyone.
Bye.